Hi students, welcome to part 2. In this section we are going to learn about simulation configuration and Simscape. So we'll first understand why it's very much important to understand about how we configure our simulation, and by configuration we mean that what are the parameters we are going to assign and how we are going to run the simulation in such a way that this configuration or this settings of the model represents the real world scenario, or we can make it more realistic. So let's learn about the simulation configuration. Before we start, let's understand what are the Simulink toolboxes, and sometimes they are also known as Simulink block set. So a block set or toolbox is nothing but a group of similar models put together. For example, if they are electrical elements like resistor, capacitor and inductor, they are put under one toolbox, and let's name it as electrical toolbox. And there are some fundamental hydraulics related stuff, there are fundamental other stuff which will be categorized as either toolbox or block set. Now this toolbox and block set are actually based on the applications. So whenever we discuss about modeling of any engineering system, we are going to discuss with specific application. So according to the type of application, the Simulink toolboxes are like this. So there are signal processing related toolboxes, and they are purely related to audio and digital signal processing. And there are certain image processing and computer vision toolboxes. There are control system toolboxes as well, and here you have a model predictive control system. Here you have a Simulink control design and design optimization as well. Now with the Simulink you can actually make a data acquisition system as well. Instrument control toolbox is also added. Another communication category is antenna and radio frequency wireless toolbox, which is nothing but a Wi-Fi or wireless LAN and 5G. And there are autonomous systems as well, where you see the automated driving toolboxes, where you see the sensor fusion and tracking toolboxes. And here you have some toolboxes related to the hardware stuff, which is called hardware description language coder or HDL verifier or system on chip block set. Now in the automotive application, these are the toolboxes which are added. So this is automotive, this is aerospace, and here you have something for system engineering. So these toolboxes are important when we learn about basic electrical and mechanical system modeling. So here you have a vehicle dynamics block set, here you have powertrain block set as well. And in this case, if you want to implement any logic, which we are going to learn in this course as well, which is a state flow. So these are the important Simulink toolboxes and block set categorized according to the application. You can visit the MathsWork website in order to again look at the another category where you have different toolboxes in a classification. So where you see the fundamental blocks, the fundamental blocks are actually going to be the part of very basic blocks, right? And then you will have a system level block diagrams. So this is also important. A system level engineering is also done using the Simulink. So with this introduction, let's start with the simulation configuration. So why simulation configuration has to be right? So what will happen if the simulation configuration is wrong, right? And what are the important parameters? Someone is interested in how does the engine starts. Some person is interested in knowing that what are the dynamics involved in starting of an engine, right? And the starting dynamics of an engine can be related to a starter motor, maybe some gearbox, and maybe some solenoid, or let's say some relay or contactor type of an arrangement, or ignition, and maybe the battery, and along with the engine with its control system. So engine along with the control system and all these parameters put together are going to end up starting in engine, and which may be taking, let's say, around 5 seconds. So this is our interest, where how does an engine start and how effectively all these components are playing their role. Now on the other hand, someone is actually interested to figure out what is the overall engine efficiency, right? So these are the two different purposes, where we have a similar system where engine and its control both are present in all these two cases, but we want to understand, or we want to study different aspect of the system. So here it's only starting, here it's overall efficiency. So overall efficiency is going to involve, let's say, the fuel type, the fuel energy content, and again the engine along with its control. So engine along with its control, how you are going to run the vehicle, right? Or how the engine is run according to its speed and torque demand. So this is going to be the case in overall efficiency. And what do you think, for how much duration we should run the simulation which is related to engine efficiency? Any guess on the timeline? Yes, it has to be definitely far greater than the 5 seconds, which is just time required for an engine to start. So the overall engine efficiency may be, let's say, 5 minutes. So we want to run an engine for 5 minutes, and within this 5 minutes we want to take the idea about what is the engine efficiency with reference to different speed and torque, and with reference to different control systems. So these two simulation configurations where the engine and control blocks are common, but their time are different and their purpose are also different. So therefore the simulation configuration is very, very important. So first you need to identify what is the purpose, and accordingly you select a timeline, and whether you are interested in the transients or dynamic, that is going to decide the overall system. So simulation configuration parameters will decide what situation is of our interest. So whether we are interested in transient, which is a kind of start of an engine, or whether we are interested in efficiency of a system, where let's say the engine is going to run at a constant speed, or we are interested in overall efficiency, or let's take the average of all number of efficiency at each point. So the simulation purposes may be different, and all the configuration parameters are very, very important. And in order to configure your simulation or your model to match with this, we need to understand very fundamental concept. So what are these fundamental concepts? So these are important simulation terminologies. So I'm going to introduce now the very fundamental terminologies for simulation. The very first thing is simulation time, and you must have observed this simulation time is nothing but actually the stop time in our case. So the stop time is nothing but what we have seen in the Simulink window, and for how much duration you want to run your simulation. So that is called a simulation time, and this is the first important parameter for configuration. The second is runtime. So if you have observed the simulation stop time, we have kept it as 10 seconds, right? And did the simulation has taken actually 10 seconds? No, it was quite faster, right? Because the model was quite simple, and it was 10 seconds is not going to be a large amount of time. Now let's say, for example, if you run your simulation for 1000 seconds, now is it going to take actually 1000 seconds in your computer? No. So runtime is nothing but the amount of actual time taken by a model to run in any computer, right? So that depends on your PC or maybe any computational device on which you are running your MATLAB, and the speed of that device along with certain other configuration parameter which we are going to study. So the runtime is another important parameter which represents how much actual time is taken by the computer to solve the model or to run the model. So this is the second important terminology, runtime. Now you are very clear about what is simulation time. Let's say the simulation stop time is in 10 seconds, and the actual time for the corresponding 10 seconds may be less than a second, right? So if your computer is fast and if your model is simple enough and your configuration parameter or your sampling time is different or let's say sufficiently high, then your stop time will be somewhat around 1 second, and this is not going to include the compilation time and other settings as well. So let's go to the next step or the next terminology, which is a sample time or time step. This is very important terminology. A sample time or time step is nothing but the time duration, or let's say a piece of time for which the model is solved on each time step. So sample time, a time step which represents the duration after which your model is solved again, right? So the model is solved frequently with the varying inputs or with the varying conditions. So after how much time your model is going to be solved again, that is called a time step. So let's say you have a total simulation time of 10 seconds, and for 10 second simulation time your step time, whatever you have configured, is 0.1 second. Now every 0.1 second in the simulation your model is going to be solved, all those equations are going to be solved again. So within 0.1 second your model is going to be solved one time. So how much is the time you are allowing your simulator to solve all the equations of your model, that is going to determine the sampling time or time step. So we are going to see this very important parameter, what is going to be the time step, right? So let's understand another important terminology which is called a parameter sweep. So let's say, for example, we want to simulate the Ohm's law for a resistor. So Ohm's law tells that whatever is the voltage across the device, that is proportional to the current passing through it, provided there is no change in the temperature. So voltage is proportional to current, and that constant of proportionality is nothing but the value of the resistance R ohms and multiplied with the I. So that is the voltage equals to R times I. R is a resistance value in ohms. Now in this case you want to analyze what will happen if the temperature is changed. So you can have an equation of resistance at a given temperature, let's say R at T. Now R at T may be a different characteristic. Let's say it's going to be like this, or maybe for different type of material, whatever is the temperature and whatever is the value of the resistance, that may be different. So if the temperature is going to increase, the value may decrease, right? So that may be the negative temperature coefficient devices. Now in short, you want to actually understand the effect of temperature on the resistor. That can be carried out by parameter sweep, where you run your simulation, let's say for 100 number of seconds, and in the 100 number of seconds your temperature is, let's say, 20 degrees centigrade for first 20 seconds. Then your temperature has been increased to 25 degrees centigrade for next 20 seconds, and you keep on increasing your temperature every 20 seconds. Let's say the next temperature is 35 and another is 45, and due to this all change in the temperature degree centigrades, what is going to be the effect on the current passing through it and the voltage across this device. So that can be understood by a parameter sweep. So these are 4 important simulation terminologies. We will learn how it can be built. We are going to learn about how this parameter sweep can be taken care into the simulation. Basically what we are going to do here is, how do we change a parameter? How do we actually change a parameter which is not fixed and while the simulation is running, and that is called a parameter sweep. So how do we change a parameter during runtime and which is not declared previously, right? So this is going to be very important when we are going to learn about real world situations and try to model the effect of change in the parameter when the simulation is actually running. So now we are going to explore the time step a bit in detail and understand about its pros and cons. So before we understand about the actual time step and what are the options for configuration of a time step, we will learn about how does a simulator work. So a simulator is going to first compile, as I discussed earlier. So the first step is going to be the compilation. It is going to be exactly the same way where your text code, or let's say your programming language, is compiled and it is going to be translated into some other language. So the translation is nothing but the compilation. So the blocks are translated into executable code, or they are nothing but the equations, right? So a simulator, before running, it is going to compile your block or compile your model where all the blocks are present. Now after this, once it is translated in the backend, equations are computed. So basically the MATLAB and Simulink is a technical computing tool where all the equations are computed at each time step and signals and states are updated. So what a simulator is going to do is, all these equations which are translated, those equations are computed at each time step, right? So every time step, this values or these equations are calculated again, and signals and states which are related to this model, they are updated. They are going to affect it, or they are going to change according to whatever are the equations fed into. So what is the meaning of a backend? So backend is something which is you are not able to see. So if you have your own programming language or a script file.m file, you will be able to see what's happening because you have written the code. Now blocks are translated into the equivalent executable code, which is not going to be involving you, right? So it is going to happen in the backend where the user or you as a modeling engineer will not know how it is translated and what has happened, right? So the backend is going to be the all equation solutions, right? But it is also important to learn what is going to happen in the backend, right? So even though, because you are not kind of a programmer, or you are not going to kind of your own program to execute another program, but you will be able to understand what happens in a backend. So it's similar to solve the equations by placing the increasing values of time instance, right? So how does a simulator work? So let's say you have an equation. For example, we have created our first file where it is 12.3t, and in this 12.3t, let's say the output y equals to 12.3t. How does a simulator work? So simulator is going to put all different values of time and calculate all different y's and plot the y. If your y or the output variable is any other complex combination, it may be an algebraic equation or a differential equation, or maybe any other complex model which is going to be solved in the backend. So all the equations are going to be solved. What is the important keyword here is a solving, right? So solving the equation is going to be the task which is happening in the backend. So how does this solving occur, right? So the MATLAB has various different types of solvers, and there are types of computations which are performed while simulation is running. So for example, if we take an equation where 2 plus 3e raised to t, and you want to compute this value of function, let's say your y is output and y of t is going to be like 2 plus 3e raised to t. So here you have a 2 default value, and now you have an exponential added to this 2, and you keep on putting all different t values, and you get nothing but a graph. So a simulator exactly makes a graph of a function. Now this function may be as simple as this, or maybe very complex as pump, where you have multiple equations acting together. This is going to be the working of a simulator in a background, or in the front end whatever you are going to see is nothing but a GUI, or a graphical user interface. So what is the difference between a continuous and discrete system? A continuous system is where the time is considered as continuous, and in discrete, where we consider the time is not continuous and there is some time gap, or there is some time difference between two time steps. Obviously, it's not possible to run any model on a purely continuous basis, but we can analyze that with a sufficient high value of sampling time, which is denoted as, let's say, TS as a sampling time. If you have a sufficient high value of sampling time, and your observation of understanding the system, or your observation of this time, is going to be a larger dimension, then you can assume that it is as equal as a purely continuous system. So this is the very fundamental difference. How do you run your blocks in the background, whether your system is going to have a continuous system or a discrete system. So let me give you an analogy or an example of a continuous system and a discrete system. So what you see here in this GIF file or an animation file is basically the needle rotating without any delay, right? So probably you and me are not able to capture any delay happening with this needle movement, and therefore we see the time to be continuous. Now at the same time, if you see a clock tick with a normal clock, which is going to be like this, and this is an example of a discrete system. So discrete system, you will have actually delay in two time step. So here you do not have any delay which is observable, but actually it is there. Here you have a delay which is quite sufficient so that you can observe as well. So this is a very fundamental difference between continuous and discrete system. So let's now understand what are the Simulink solvers. So here there is a library of solvers, and according to whatever is your model type, your solvers will be decided. So let's understand what is the hierarchy that is followed in choosing the solvers for your simulation. So here is a flowchart or a graph which will help you to understand what are the types of solvers. So do you have a fixed step solver? Then yes. And is your model having continuous states, or is your model having discrete states, right? So then you have a fixed step discrete solver, and if yes, in case of a continuous states, then it is going to be fixed step continuous solver. If it is not going to be a fixed step solver, then it is called a variable step condition over here. Now let me explain you what is the meaning of fixed step and the variable step. If during your simulation, if your step time remains same, right? Let's say you have a total simulation time of 10 seconds, and in that 10 seconds your step time is going to remain fixed as 0.01, let's say for example, and it does not vary throughout all this 10 seconds, then it is called a fixed step condition. Now sometimes you may require to have a variable time step, because during transient you want to have your step time to be very low, and during steady state you may require your step time to be very high, so that your overall runtime is going to be sufficient so that you can run your simulation quickly, right? So in that case the variable solvers are required. So the variable step solvers will inherently change the step time. Now who is going to change the step time? So the MATLAB itself, or in the backend, it is going to take care of what is going to be the step time. So now the step time is not fixed, it's going to vary according to your configurations and the way MATLAB treats the model. Here also you have another two categories, which is variable step discrete solver and variable step continuous solver. And here you have a fixed step continuous solver and variable step continuous solvers. They are classified as different names, and these names are nothing but ODE, which stands for ordinary differential equation of first order, second order, third, fourth, and so on, right? Here you have a variable step continuous solver, ordinary differential equation solver of 15th order, maybe 23 order, and the S and T stands for stiff or non-stiff. So these are Simulink solvers. Sometimes actually you need not to worry about what is going to be the solver, because you can choose the auto both in terms of choosing a solver as well as the step time. So when you make auto, the Simulink in the background is going to take care of what type of simulator or what type of model you have, what type of blocks you have, and it will be adjusted automatically without compromising the accuracy of the model. So how does an auto solver work, right? So the auto solver is going to decide whether it's fixed type or variable step type, right? Now if your system has only discrete states, then it is going to be fixed step discrete or variable step discrete. Now if your system is going to have the continuous states as well, then it will be either of these four category depending on the fixed step or variable step. And based on the automatic solver configuration, if you have a fixed step configuration and you have a continuous state with ordinary differential equation, then it is going to be ODE3. If it is going to be a differential algebraic equation, which is DAE, then your solver is going to be ODE14X. So whether your model is stiff or non-stiff, that is another different category. The auto solver is going to assign this type of equation solver. Now what is basically a solver? A solver is nothing but a software, or we can say a code written in order to solve your equations, right? So a solver is nothing but a program, or we can say a software or a code which is written by the MATLAB engineers, where your model is going to be solved based on this program, right? So if you have heard of basic differential equation solvers and the methods, which is a Runge-Kutta method or maybe Euler's method, these are nothing but the mathematical techniques or the numerical analysis which is going in the backend. So this is about auto solver. Now what are the Simulink data categories? Now how does the Simulink treat the data, right? So these categories are very important. The first category is a signal. Signals are nothing but the block inputs and outputs computed during the simulation. So this is one category, and signals which are nothing but inputs and outputs, and they are computed during the simulation. They are going to change, right? So it's possible for you to change the inputs as well, and outputs will be also changed accordingly. Another data category is states. Now states are nothing but the internal values representing the dynamics of the block, and they are also computed during the simulation. So they are not the final outputs, not the predefined inputs. They are nothing but the internal states or transition values from one point of time to another point of time. The other category is nothing but the parameters. Now parameters is nothing but the values that affect the behavior of a block, and it is controlled by the user, right? So the user has to give some input parameters. So for example, let's understand what is the meaning of all these things, right? So let's say we have taken a block in the Simulink which represents an engine, and there are some multiple inputs and there are some multiple outputs, right? So all these are called signals. So the input things are called signals, and again outputs are also signals. Now whatever is happening to the engine inside because of this input signals, they are called the states. So states are nothing but the values of signals at each point in the engine block, right? So if you explore the engine, what is inside the engine block, you will have all multiple different types of blocks, and all those signals at multiple types of blocks represents the internal state. Now what are the parameters? So the parameters are nothing but how you assign the values and which does not get affected during the simulation. So parameters are nothing but, let's say, the horsepower of an engine, or let's say the value of the maximum speed of an engine, right? So maximum speed, the horsepower, maybe the torque, and any other parameters which are fixed or which does not change while the simulation is running, they are called as parameters. So we need to differentiate between all these three very clearly. Basically what Simulink is going to do, Simulink is basically going to compute the new values from the signals which are given as inputs and the present states, and it is going to create all new variables. So if you specify the parameters when you are going to build the model and can occasionally change them while the simulation is running. So it's also possible to change your parameters while the simulation is running, and which is exactly the same thing we discuss as parameter sweep. So it's also possible, but it's not always, it's going to be occasionally. So what are the Simulink model options, right? So sometimes we are discussing about the engines, right, which is a very complex system. Sometimes we are discussing about RLC parameters related to electrical, or spring, mass and damper related parameters, which are basic building blocks of mechanical systems. So what are the options? So is it possible both the ways? So yes, the answer is yes, you can do both, right? So the Simulink model options are possible where you have a very complex system readily available, as well as you have a very fundamental block so that you create your own engine model as well. So it's possible in both the ways. The first thing is the fundamental block, which are nothing but spring, mass and damper, or maybe RL and C in electrical engineering case, and other is the ready-made system block. So the ready-made system block is nothing but the engine, or you can have a gearbox or something like that. So this is going to be like a Lego block, right? So where you have the fundamental blocks are Lego blocks, and it's up to you what kind of system you want to make. And now you can actually create your system, and you may have a multiple number of subsystems as well. And the ready-made blocks are nothing but like this, where you have part or a system which is ready, which will look like something this, or which will behave in a certain way, right? So these are readily available blocks, and you can pick them and place in your model, or you have also an option that you create your own model. So initially, as a beginner, we are going to go ahead with the readily available blocks, right? So that our task is going to be easy in order to run a simulation. Now let me give you some introduction to the Simscape. So Simscape is something where it's readily available library. What you see here is an equation of the acceleration, velocity and the displacement, and these are nothing but the integrator 1 over s. They are called the integrator, and m is the mass, this is b is a damping coefficient, and k is a stiffness coefficient of the spring, and this is how you get the value of the x. Now the same system in Simulink will look like this as a block diagram, and in Simscape you can take up the mass block, damper block and spring block readily available, and apply some force to this model. So this is going to be a very simple thing, right? So Simscape is going to be actually related to the physical simulation. So all physical simulations are now part of the Simscape library. So Simscape library is recently built by the MathWorks, and it is nothing but all physical signal simulations, or it is actually covering everything: electrical, mechanical, electromagnetics, maybe thermal and fluid, and so on, right? So Simscape is actually covering all physical simulations. So now it's the time to start our simulation and understand how does a system model works, or how we can step by step create the model. So we are going to take an example of a lever mechanism. What is a lever mechanism? So fundamentally, a lever mechanism is going to have some kind of an arrangement, or let's say this is a metal rod and it is going to be fixed at this point, right? So let's say a metal rod is having length A, B, which is a total length, and C is going to be a point from where it is fixed to a point, right? Or where it can move when you apply some force in the downward direction from this A is going to go upward, right? So this is a basic lever, or called a linkage mechanism. And let's actually build a lever mechanism simulation in the Simulink. So for more clarity about the lever mechanism, if I shift this C point to the middle, right, or where exactly the case is AC equals to CB, if both the lengths are equal, then it's going to be a typical case of a seesaw, right? So this is going to be the typical case where it's a seesaw, and this is point A over here, B over here, and AC and BC, both the distances are going to be same, and C is going to be the fixed point, right? So whatever is a force applied, that will be translated to the point B, and this is going to be a very simple lever mechanism. So let's explore Simulink for lever mechanism.